Salam, everybody. Welcome to Physics with Noshir. We're discussing this paper. Let's have a look at the first question. So, you're trying to balance this ruler. You can see that the pivot is not at the middle, so the weight will be somewhere here. And you're trying to balance this ruler with these rings placed at the 5 centimeter mark. Now, they're saying that the rings are circular with the central hole as shown, and you have to measure the diameter of the ring. Now, how to measure the diameter? Make sure that you start from this line and you end at this line. These are your vertical guidelines. You have to measure this length. This is the diameter, and does not matter whether your answer matches the marking scheme or not, because the printing mechanism for Cambridge could be different from a regular printer that you use at home. So, as long as you're measuring this length, you're good. This length turns out to be 1.7 centimeters. Now, they're saying you have to draw one ring placed correctly at the 5 centimeter mark. So, what did I do? I divide the diameter by 2, I got 0.85. I divide by 2 so that I could get the center of 1.7. Now, the center of 1.7 is 0.85 centimeter from either side. So what do I mean by that? If the center is 5, then I will subtract 0.85 from 5, which is 4.15. One edge of the coin should be at 4.15. And then I can add 0.85 to 5 to get the next edge of the coin, which is at 5.85. So when you divide 1.7 by 2, you get 0.85. You know your ring has to be placed at 5. So if your ring has to be placed at 5, you should know that you have to subtract 0.85 and add 0.85 to get the edges of the coin. And then you just make the coin on the ruler and make sure that it's placed at the 5, because as you saw in the question above, it is placed at 5. Explain why the student adds the rings carefully one at a time. This is to ensure that the right number of rings are gotten through this experiment. If you do the experiment in haste, let's say you put 15 rings at one point, maybe it doesn't balance. Maybe you put 3 rings, doesn't balance. So you will get that balance very, very slowly, and that can only be done by putting one ring at a time. And if you move on, then they say the distance L between the pivot and point A is changed by moving the pivot closer to A. So the student is repeating the experiment and he is moving the pivot closer to point A. So he's moving the pivot this way, and due to that, the number of rings that you need in the experiment are changing. Now, they've done the experiment for you. First, the length was 40, now the length is 35, then 30, and you can see that the number of rings are increasing as the pivot gets closer to point A where the coins are placed. The first question is draw a graph of n on the y-axis, L on the x-axis, start from 0, 0, draw the best fit curve. A couple of points that you must note: that first of all, 3/4 of the graph should be covered. Number one. Number two, you should never draw jag lines. Jag lines are lines like these on the x-axis or the y-axis. Usually do this in math, but in physics, please do not do it. No jag lines are allowed. And if they're saying start from 0, 0, they mean start from 0, 0. And when they write best fit curve means that the curve should be very close, should be as close as possible to all points, as close as possible to all the points. That is what we mean by best fit curve. Now, some points could be above, some points could be below, some points would be on the line, but your curve should be very, very close to all of the points if there is no error in the reading. Now, let's have a look at the graph and then continue the question. When you look at the graph, this is what the graph looks like. Let me squeeze it in the screen. I hope that you also make the same graph. Please do try this yourself as well. Starting at 0, 0, took intervals of 5, 10, 15, 20, 25, 30, 35, 40, and then 10, 20, 30, 40, and so on and so forth. N slash no units on the y-axis. So you can even leave it as n, and you can just write n because n has no units. On the x-axis, however, you can see that I've got L, so I should be writing L slash centimeter. Please remember I've written it. Let me show it to you. I've written it, but I don't want to change my screen. So L/centimeter, N on the y-axis, and just remember, whenever you're giving the label, it's always the label/unit. If you do not write the unit, you will not get the mark. And then you can see this curve. This curve is covering more than half of the graph. How do we know? This is your graph size, right? So this is the center of the graph, and this part is in the part beyond half. So 3/4 of the graph has been covered. Got it. And then you have plotted these points. You can see this point is close, but it's not on the line. That's fine. This point is close, not on the line. That's fine. Your points have to be very close to the graph. That is the line of best fit. Now they said that when the length is 18, figure out how many coins do you need. So for 18, when the length is 18 between the pivot and point A, the number of coins that we need are 51. That is the reading that I got from there. So let's go back. And here we go. They say use your graph to estimate the number of rings required to balance the rule when the length is 18. Let me zoom in again. The number of rings that I got were 51. Any answer between 50 to 53 was accepted. Theory suggests that mass m of the meter rule is given by this expression, 3.3. What was this 3.3? If you go back to the start of this question, let's go back. Go back to the start of this question and you will realize that actually 3.3 grams was the mass of each ring. So 3.3 has units gram. N has no unit, N is number. With the number was 51. So you see beyond 51, I haven't written anything. L is the length. The length was 18 centimeters. Where is this written? This is written over here. The length is 18. So the unit for length is centimeter. What was 45? 45 was again your length, initial centimeters, and this is also centimeters. So when you're plugging in your values, 3.3 is grams, 51 has no units, 18 is centimeters, and 45 minus 18 are centimeters too. So centimeter and centimeter will get cancelled above and below. And when you calculate the value, you'll get 112.2. Remember, your answer has to be in 2 to 3 SF, so you'll get 112, and the unit that is left is grams. Name a piece of apparatus that can be used to check whether the theory is correct. You're trying to measure mass, so it's the top band balance. Suggest one way in which the method of measuring the mass of the meter rule can be improved. Now, please remember that the way to improve your readings is, or to improve your result is to take more readings. Now, how do you take more readings? I've already gotten to a very small length. What do I do more? What more I can do is I could use rings of different masses or smaller masses, because when I'll use rings of smaller mass or smaller size, what's going to happen? This length is going to change, the number of rings are going to change, and as a result, I will have more data for my table. I'll have more readings here, more readings here. I'll have more readings to plot my graph. And when I'll have more readings to plot this graph, obviously my answer is going to improve. So one way in which this method of measuring mass can be improved is using smaller rings or using rings of small masses and large masses. Now, one thing I'd like to mention before I start question number 2 is usually whenever they're asking you for improvements, if you have drawn a graph, then remember average will not have an impact. That's why I did not write take an average. Remember this. If you're writing take an average and there's a graph drawn, you will not get any mark. If the graph is not drawn in the question and they ask you how do we improve the results, you can take more readings and average, and you will see this as well. Now in this experiment, you want to find the resistance of a filament lamp and how the potential difference across it changes. So you put a voltmeter across the filament lamp and you put an ammeter in series. Ammeter could be here, here, anywhere in series because the current remains the same. How he adjusts his circuit to do this, he changes the resistance of the variable resistor. Another way is you could also change the number of cells to change the current, and that can give you different readings of current and potential difference. He adjusts his circuit so that the voltmeter now shows 4 and the ammeter reading he reads. He repeats the experiment at 8 volts. So this is at 4 volts, this is at 8 volts. At 4 volts, the reading is 1.2. This is 1, 1.1, 1.2. At 8 volts, this reading is 1.5. This is 1.6 and this is 1.65. Now remember, if you're in 1.65 over here and you wrote 1.2 over here, you're losing marks because you're not measuring to the same precision level. It's the same ammeter, right? If you're writing this to 2 decimal places, make sure that you write this to 2 decimal places as well. That is why I wrote it as 1.20. Use the expression R is equals to V over I to calculate the resistance. So when voltage is 4, the current was 1.2, so you got 3.33 ohms. And when the voltage was 8, the current was 1.65, so you got 4.848. So I wrote 4.85 ohms. Make sure you don't forget the unit. 2 physical changes. Physical changes mean something which you can see, something which you can feel. If you end up writing that when the potential difference is increased, the resistance gets more, that's not a physical change. You can't see resistance. But how do you feel it? You'll feel it because the lamp will be brighter when the voltage is increased. The lamp will be hotter when the voltage is increased. And remember this, that as you increase the voltage for a filament lamp, what is happening to the current? The current is also increasing with it. So if somebody asks, what will be the effect if current is increased? Same effect, because with voltage, current is also increasing. The lamp gets brighter and it gets hotter. And this, by the way, is the graph for a filament lamp. Let's have a look at the third question. You have a beaker, you've got these marbles, and then you put some water as well. Now try to understand that when no marbles are present, I'll show you the first column. When no marbles are present, this balance is still showing you a reading. Why is it showing you a reading? Because it's measuring the mass of the beaker. So this reading over here is the mass of the beaker. Remember this. Then what he does is he puts one marble. When he puts one marble, the mass, obviously reading changes to 23.27. The question is, what is the mass of the marble? So the mass of the marble will be this minus this, which is 5.67. And the reading of the measuring cylinder was 40 cm cube without, when you put water inside, the reading of the measuring cylinder was 40 cm cube. Then when you put one marble in, the reading of the measuring cylinder went up to 42. So what is the volume of the marble? The volume of the marble will be 2. Then what happened was they increased the number of marbles to 2. When they increased the number of marbles to 2, obviously the reading on the balance went up. Now, how do you get, what is the mass of the marbles? What is the mass of this beaker? The mass of the beaker is 17.6. So 29.31 minus 17.6 gives you 11.71. And similarly, with just the water, this is, let me write it down. This is the mass of the water, just the water. So with the 2 marbles, the volume is 45. So you do 45 minus 40 to get the volume of the marbles. And that is how you get this table. Every single time you want to calculate, you have to subtract the mass of water to get the volume of the marbles. And every single time you have to subtract the reading from 17.6 to get the mass of the marbles. And if you notice, all of the readings are to 2 decimal places, all of the readings are to 1 decimal place. Remember, down the column, your number of decimal places must be the same, down one column. It's not necessary that both columns should have the same number of decimal places, because this is volume, this is something else, this is mass, this is something else. But down one column, the number of decimal places should be the same. 0, 0 do not count, because that means there's no reading. Now, when you try plotting these values, it might be difficult. So here's what you do. For plotting purposes, when you're plotting the graph, you can round them off to 1 decimal place. But in the table, let it be to 2 decimal places. So I'll show you the graph. This is what the graph looks like. And you have the mass in grams. Look at value slash unit, value slash unit. And if I've plotted the values for you, I've rounded them off to 1 decimal place, and that's how I got my results. And now I've taken this value and this value to calculate the gradient. What will the gradient of this graph give, by the way? The gradient of this graph will give me density. Why? Because gradient, as you all know, is rise over run. And what is on the rise axis? On the rise axis, you've got a change in mass. And what do you have on the run axis? You've got a change in volume. So what is mass over volume? Density. So the gradient of this graph gives you density. So remember that whenever they ask you to calculate using the graph, and you have to select 2 points, you have to make sure that you write the coordinates of those 2 points, and you also make a triangle between those 2 points. The examiner, remember, the more easier you make it for the examiner to check, the more the marks that you will get. This is so common sense, and you're just playing with the psychology of the examiner. If you make it harder for the examiner to check, what will happen? You'll get less marks. Make it easy for the examiner to check. So the examiner would like to see what 2 points you've taken for your gradient. So why not show those 2 points to him on the graph and make a beautiful triangle in between? Doesn't take much effort. And do not forget to write the units. Y2 minus Y1, this was change in mass. So you wrote grams over here, and x2 minus x1 was volume. So cm cube, you can write g over cm cube, or you can write g cm minus 3. Then they ask you to identify the type of glass used. So in the table, if you go up, this 2.53 value is closest to zinc crown. In part E, they're saying, why don't you measure the volume first? Because if you measure the volume first, you see, guys, water would stick to the marbles and then the mass would change. So that is why you measure the mass first before measuring the volume. Why do you use 100 cm cube? Because you don't want the water to overflow. Just imagine that I have a 40 cm cube container, which is a cylinder, which is filled to the brim. And now I put a marble in, what's going to happen? Water will overflow. So remember that your cylinder should be large enough for the water and the marbles to be comfortably placed inside. So that is why you use a larger cylinder. Now you have this volume of a sphere formula. They're asking you, how do we find the volume of a sphere accurately, or a marble accurately? So to measure the diameter of a marble, you will use a vernier caliper, and from that, the reading that you'll get is the diameter. What it'll do with the diameter, it'll convert it to radius by doing diameter divided by 2, and then you will use the formula volume is equals to 4 by 3 pi r cube. Worth mentioning over here is you should also know that the surface area of a sphere is given by 4 pi r squared. Do not forget that. And in this question, you are investigating the way seeds fall from some types of tree. And to do that, he uses a paper with a weight at the bottom, and he cuts it from the center halfway to create wings. The wings are going to block air as you fall down. So that is going to give you some modeling of air resistance. Question number 1. The question is two variables that could affect the time of fall. He's already saying that I could vary the length of the wings. So besides the length of the wings, he could play with the mass of the paper clips, or he could use a different number of paper clips that could affect the time of fall, because if you increase the number of paper clips, it will fall quickly. You could also change the height from which this thing is falling, right? So if, let's say, this is the ground and you're making it fall from this height, let's say next time you can start from here. That can also change the time that it takes you to fall to the ground. You could also add more paper clips. You could even use less paper clips, but which are heavier. So change the mass of paper clips. All of these points can be written. You just have to mention any two of them. So more paper clips, height from which it is dropped, weight of each paper clip, and of course the surface area of the wings. So they change the length, right? We're saying you could use broader wings. So if you use broader wings like this broad and that broad without mentioning length, that can also be a very valid point. In the next part, they say how changing the length of the wing affects the time taken. Now, if you increase the length, what's going to happen? If you increase the length, are you going to block more air or less air? Let's remove the area parameters and let's just talk of length. So if I have more length, which means I increase the length from here, increase the length from here, am I trapping in more air or less air? The answer is I'm trapping in more air. So if air resistance is increasing, what's going to happen to the time of fall? It'll take me more time to fall. That is why we have said that when the length increases, the time taken will increase. One possible way of improving the accuracy, repeat the experiments and take average, because I told you earlier that in this question you haven't plotted any graph. So what's the way? You take more readings and take the average. You repeat the experiment and take the average.